we're going to finish out our linear inequalities. Then for today, our new stuff, we're going to just expand it a little bit bigger. Our quote today is, "Only those that attempt the absurd will achieve the impossible," by M.C. Escher. I love Escher. I have a whole book on Escher. I'm going to show you some things that I love about Escher. Okay, so Escher, M.C. Escher is, you might know who that he is, or have you heard of M.C. Escher before?
I think so.
Okay, so maybe some of these will jog if you're like, hey, I've kind of seen that before. So he was absolutely kind of like rejected by the art community. However, he was revered by mathematicians because he was known for making the absurd believable, like in this way, like the realism of making this. This is a really famous one. So the trickery in this drawing, that no matter where you look, they're all going up, but they're also all climbing down. So to be able to look at, the way that he drew the stairs where they're climbing up, but then they're also climbing down, and to merge that. There's another one that's a waterfall that, where it's like this, and it's a waterfall, and it's falling down, but it's also going up. Yeah. It is an Escher one as well, so there's a lot of mathematics involved in it. This one I love. It's like the checkerboard one. And so the birds are flying into it. This is neat because it's also a geometry skill of tessellations. Is a fun project that you can do with it. But he used math and arts all of the time. So I love Escher. Okay. So for today, we're going to take what we just did with 2 guys and 2D. We've gone from a point to a line to a coordinate plane, and now we're going to go 3D. We're going to add Z to it, and we're going to make it real life, okay, for it. And so as we are working in the 3D coordinate plane, we're going to have to talk about the way that we identify our plane values will actually change a little bit. Okay, so we're going to learn how to actually graph a coordinate in the 3D plane. We're going to be able to still rearrange an equation for whatever variable we want to, go back over function of, but we're adding a variable to it, right? So we're learning how to read that. We're going to find the solution of a system of 3 equations instead of 2, and then the inequalities, that's the same, and we are even going to go over some linear programming, possibly. Let's see. Okay, so graphing in 3D, we started 1D was one-dimensional, just the plane. 2D is 2-dimensional. It's our coordinate plane that we're looking at. 3D means that we now have an X, Y, and Z. And I have these fun little graphs that I forgot to bring for you guys. Oh well. I'll show you how to make it. And the thing that is different is that now we're looking down on it, on our coordinate plane. And so if you notice, our coordinate plane has gone up and it has laid down. So our X and our Y axis are now our horizontal ground. They're the ground level that we work on, and our Z is coming up. So basically it's like we're walking around on the X and Y axis, and the Z is what's coming up.
Or going down.
Or so it's both.
Okay.
But it's that vertical.
Yeah.
So instead, a lot of times it's easier to go, oh, well, this is still X, this is Y, and Z is now here. But they're actually laid down that way. Typically, they're going to be labeled so that you know what.
So it's like X would be here, Y would be here, and Z would be like that.
And positive is still left and right. So this is positive, this is negative. This is positive, this is negative, and X coming towards you is positive and going away is negative.
Okay.
All right? So a little different for that. Okay, so we just talked about that. It's laying down. How we write it is still a coordinate point, and it still goes alphabetically. Oh, isn't that nice? Same. X, Y, all we're doing is tagging on a Z at the end. So it's always going to be X, Y, then Z, written in parentheses with your commas between both of them. Okay. our standard equation looks just like our regular standard equation, except we have now added a third term in there, right? So we can still rearrange everything the same. We can still solve for it the same. We just have an extra term. We've just expanded it a little bit more. Okay. So now here's our question that we were talking about. If we have 3 variables now, how many equations do we need to find an actual number answer? 3 equations. Perfect. 3 variables means we actually have to have 3 equations to be able to solve it, right? So when we solved our regular 2D ones, we could just plug it in, right? We had it this way, y equals x plus 3, and we'd say when x equals 2, we plugged it in that way. We would solve, it gave us a coordinate point. We could also write it as this, f of 3, because this is the same instructions that is saying when x equals 3. Yes. Then we knew what to plug in, right? So those are all our vocabulary that we have learned. So in this same way, for 3 variable solutions, it's still a coordinate point. We still get to write them and solve them all the same. So if I've got 3x plus 2y plus 4z equals 12, we're going to always write out our empty coordinate point at the end just so that we make sure we get all the guys. We don't leave somebody out, right? So x is what when y and z are 0. So these are intercepts, right? What did we ask when we found an x and y intercept on a regular coordinate plane? Regular coordinate plane. To find the y-intercept, it answered the question when x equals 0, right? And to find the x-intercept, we answered the question when y equals 0. Well, now I'm trying to find the intercepts for z. So if I'm looking at, I'm going to add this guy in. If I want to find where it crosses the z-axis, both my x and y have to be 0. Does that make sense?
Yeah.
So we've just expanded an axis. Instead of saying when x equals 0, z equals what? It's now when x and y equals 0, z equals what? So to write our intercepts, we write our coordinate point in. We should have 2 zeros in it. So for this one, when y and z equals 0, x equals what?
4.
Yeah, so we just took out both of those and we said x equals 4. Yep. So our y-intercept is 4, 0, 0. Okay. So we ask the same question for y. When x and z equals 0, y equals 6. So here's our coordinate for that one. When when x and y are 0, z equals 3. Okay, so now we know where all of these lines are crossing. Okay, now we could also rewrite this equation for any other variable that we want. And the terminology that you will use is rewrite it as a function of. Okay? Remember, of is multiplication, right? So a lot of times we've got function of x, we can think of it like that. You can read it the function of. So we are looking for this variable. Well, when we had that variable in the front, that means that's the variable that we're actually going to plug in, right? So I'm solving for the other guy because that's the variable I want to leave because he's the one that's plugged in. So it says our variable's already chosen for us, and so it's telling us what variable we will be replaced by a number. So it means we want that variable left in the equation, okay? Yeah. So if we're rewriting this function as a function of x and y, that means we want to leave x and y in our equation. So we're going to solve for z. Okay? So same rules that we've always had. Z wants to go to the movies by himself. Who are we going to get rid of? Everyone that's not around him. Right? So we want him by himself, so we need to move y over. We need to move x over.
And then divide 4.
Right?
Wait, so this is essentially getting slope intercept form of z?
No, it's not slope anymore because we're working in 3 dimensions.
Right.
So it's not a line anymore. We're just learning how to rewrite a multi-term equation for any variable.
Okay.
So we're solving for it, but the important thing is the terminology and the vocabulary for this.
Mm-hmm.
You will see this in greater math classes or on the ACT, things like that. So rewrite it as a function of x and y means I'm solving for z. Because function of x and y means I want to keep x and y in my equation.
So would it be if
Okay.
it was a function of, is it possible for it to be a function of x and z? And then
Yeah.
you would just be solving for y?
Then we'd be solving for y.
Okay.
Yeah, they're telling you what guys you want to leave. So we've moved them all over. We've divided. In this case, I actually just, for the one underneath, I just swapped them.
Yeah.
This way it was easier to go that way.
Yeah.
And then divide by -4. So I have z here is by himself is equal to 3 divided by -4, so -3/4 x. 2 divided by -4, which simplifies to 1/2. And then 12 divided by -12 divided by -4 left me 3. Okay? So I've got it in this way. I could rearrange it. So now we used to solve for y, and this guy we solved for z. Okay? So I would write it in this form. This is what's important to see. A function of x and y means I have x and y in my equation. When I solve and I plug this in, what value is it giving me? Z. So this guy is equal to z. Okay? So whereas we said y is equal to f of x, y was another, f of x is another angle right y. In this way, when I say f of x and y, it's another name for z.
Or you could just write down z. Like it doesn't necessarily matter.
Yeah, you could write z is equal to this and then just plug in when they give it. But you will see.
That's what you want to see them.
Well, but they will say, given f of 1, 2, what is da 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 da. You need to know what you're solving for.
Of that,
Yes.
yeah.
Okay, because you will be given the values in that
just
terms.
plug it in like normal.
Yep, and then we plug it in like normal. So again, nothing new. We've just kind of expanded it, just a little bit bigger. Okay, so again, if we were going to evaluate the function that we just had, so this is the same equation we had on the last slide, and we're going to evaluate it f of 1, 3. What does that mean?
X
Plug in
equals
x
1,
equals
y
1,
equals 3.
where the x would be,
Perfect.
y would be.
So we have x and y right here. So everywhere I see x in my equation, I'm going to place 1. Everywhere I see y,
3.
I'm going to put 3, and then I'm going to solve it, and I get 3/4, and that means my coordinate point for that solution is what? What was my x value?
Well, I mean, 1.
1. What was my y value?
3.
Now what is my z value?
3/4.
3/4. So this is my answer.
Okay.
For 1, 3, y is 3/4. That's what we're plugging in. So we were given this guy. We were given 1 and 3. We just didn't know where he
Let's see
crossed the
what's
third
there.
one. Okay? So if we were to write that or plot it, we would go to x equals 1. So we're coming towards us 1. We'll start at the origin. We'll come towards us 1, 2, 3, like that. Come 1. We're going to go along the y-axis 3. 1, 2, 3. So I've got 1, 3. So this would be where I would have it maybe in my original thing. And now I'm going to go up by 3/4. So going up, I'm going to make him about right there. Okay? Does that make sense for graphing? Now, we have got this cool guy. Let's pull him up. See what he'll do. All right, so here's our 3D plane. which we can see we've got our x-axis, our red axis, our green axis is our y-axis, and our blue axis is our z-axis there, okay? So we move around. So if I plug in that equation that we were just looking at, 3x plus 2y plus 4z, what it makes is instead of making a single line, what has it made?
Like a big square.
It actually goes into infinity in all directions. So instead of being a single line, we now have a plane. We have a full plane is what we've done. So here you can kind of see the little blue line. If I just had a single, 2 dimensions, it would be a single line. But now I have all 3 dimensions, so I'm actually looking at the plane. And what we are finding is when x was 1 and y is 3, where do I have to go to hit that plane? I'm trying to find a point that sits inside of this plane, right? So I'm going to have a little dot there. So we've actually graphed it and say, look, there it is. It's right inside that plane. Right there, you see it?
Yes.
So it is sitting inside. So that's why we have our 3D, is we're looking for the space inside those planes, and we've got all 3 parts of it that we've got to deal with, okay? So that's a fun one. Let's go back to, well, I guess here we go. Right, so when we are writing it, we would, this guy right here, 3x plus 12y plus 5z equals 30, so the new equation. And it says, write this function as a function of x and y.
Still solving for z.
Yeah, so we're going to write it function of x and y right here means that we're solving for z. So how do we get z by himself? The reason I have it where I'm just showing these 2 guys swapping is instead of moving a whole bunch of things, it's easier to just move one. Right? So if I want z by himself, I'm just going to move him to the other side. We'll switch places. So now I have my 3x plus 12y minus 30 equals negative 5z. Divide everybody by 5.
Negative.
By negative 5, yes. So in this case, I didn't really want to deal with a bunch of fractions. So I just popped the negative 5, dividing by negative 5 out front as a negative 1/5. Right? Do you see what I've done here?
Yeah.
Instead of saying negative 3/5 and 12/5 and 6, I've just moved him out front, multiplying times a negative 1/5 for it. And so it can be left in that form as well. Or you can distribute him out. Either way, okay? So now we have rewritten it as a function of x and y, right? So if we wanted to evaluate for negative 2, 2, what does this instruction tell us? What is negative 2?
X, yeah.
What is positive 2?
Y.
Y. So everywhere in this equation that I see x, I'm going to replace it with,
Negative
okay? Everywhere I see y,
2. Positive 2.
positive 2. So now I just plug it in, I work through it, and I get 12. Well, is 12 a full answer all by itself?
No.
No, it is actually a coordinate. So we were already told that when x is 2, and when x is negative 2, when y is 2, z
It's 12.
must be 12. And if we were to graph it, that point would lie in that plane
Okay.
for it. Right? Easy breezies? Okay, so now we can do that as, we can make our own system of 3 equations with word problems. Yay, right? So let's look at this one. You're making bags of trail mix called Gorp. Do that one, good old raisins and peanuts. The raisins cost $2.25, so we're gonna underline, highlight our information, right? Peanuts cost $2.95, and the packages of bags, so the bags themselves cost $2.65. So write a model for the total cost as a function of the number of pounds of raisins and peanuts that you buy. Okay, so my total cost, let's write that in words. My total cost is going to be what? My peanut cost
plus the raisins plus the bags.
plus the bags. Okay, perfect. So let's put numbers in there. So my total cost
So
is what? How much is my peanuts?
2.95.
$2.95. We'll call it P, right?
Plus
And how much is my raisins?
225. BR, I guess.
Okay, 225R. Good job.
And then plus 2.65 B.
Now, is that? Do I need multiple packages?
Yeah. Show me back.
No,
Yeah. So does this have any variable that it's multiplied by?
it doesn't need to be.
No, it doesn't have a variable that it's multiplied by. All right. So now we do have our equation. It has 3 different parts in it, right? And then it says evaluate the model for 5 pounds of raisins and 8 pounds of peanuts. So I could say my function of, if we were doing, let's do PR, we'll do it in alphabetical order. So peanuts would be what?
Peanuts is 8,
Raisins is?
5.
So I would rewrite it like this. A function of 8, 5 does what? It tells me everywhere I see an,
A P,
P.
for peanut, it would be 8, well multiplied by 8.
yeah,
And then for raisins, it'd be multiplied by 5.
okay. So now that we have that, can we solve it?
Pretty
Yep.
much.
Yeah, we don't have any variables left,
Cool.
correct? And it will give us our total cost. But now we had it as a function of peanuts and raisins.
Okay.
Okay? Right, now, so spatially, we showed a little bit. Why else is it helpful to be able to graph something in 3D? Okay? So if I have this point, 4, 7, 2, I go up 4 on my x-axis, over 7 on my y-axis, and then up 2 on my z-axis. I've got this guy here. Okay, why is that helpful? Well, if this point was a vertex of the volume of a rectangular prism that was centered at the origin, because that might be an ACT problem I've seen, for it, what is the volume of it? Well, we get all of the information that we need from this one point, right? Because if he's centered at the vertex, that means, centered at the origin, that means he's down here at 0, 0, 0, right?
Yes.
Okay, so if his x was 4, what does that give us about this rectangle? This side length
It's 8.
is
It's gonna be 8.
is
right.
4,
Wait, if it's centered. So wait, centered meaning that.
not centered at 0, 0. His vertex. is
Okay,
associated
so
with
where
the-
the I guess that would be the far side, where it crosses or ends is at 0, 0, 0.
Mhm.
It doesn't go another 4.
Correct.
Okay.
Yep.
So yeah, the side length would be 4.
4. And then what is this side length?
They said it
Well,
was
What axis does this follow along?
the
the
Y.
y-axis.
The y-axis. And what does it tell me about y?
It's
7.
7.
Y was 7. Okay, and then what is our height?
This is
2.
Is 2. Can I find the volume of that?
Yeah.
Yep.
Yeah. 8 times
Okay.
7. 56. Right? So from one coordinate, I was able to tell you all of the lengths of the sides of the rectangular prism that was formed there and find the volume of him. Right? Lots of information for it. So that's why that's an example of something that you can find. And then I do have a picture of what that looks like in the 3D, 'cause I think it's cool to see it. So if our y was 7 and our x was 4 and our z was 2, right? So we were looking at that, and then we're going to put our little point in there. So we've got our guy. and we can see that, like, if he's right here on this back, he's filled up this space and this space, right? And then he's also filled up that space because he's come up that high off of it, right? So we've got that that space that he's filling up if it's coming off of the origin. Now, why is this important? Because this is about what we're about to start finding it, okay? How do we find where all three of these planes meet? Because that's what we've done.
Wouldn't it just be the origin? The vertex?
Okay, well, so now we have, instead, if we had two lines right here, right? What is their solution? Where do they meet?
Right.
At the intersection point. But now we have three planes meeting, right? We have this, so we looked at the top two. We know that this top one and this sideways one meet along, you can kind of see it, this line right here. So where they meet forms a line in there as if you were, intersecting it.
Yeah.
But now we have this guy that's slicing it across the center. So where does he meet? Well, he meets this guy along this line, right? And he meets our x-plane along that line, and they all meet right there at that one point. Okay? So as we move through our next section is going to be solving these systems, we are looking for the point where all three collide. Okay? And now, is it possible to choose a point on this that works for two of the planes but not for the third one? What if I chose this guy right here? He would work for the Z and where are we at? The Y, right? But is he a valid point for our X guy?
No.
No. Okay, so it can be valid for two and not the third. We can have somebody over here, right? He's valid for Z and X, but not for Y, because Y is back this direction. So we can have it valid for two. We are going to be looking for where's the point where all three of them collide.
And that would be the solution.
And that would be our solution. Okay. Let's do this. Right? So as we solve, here's a couple of examples down here. We can have a lot of different ways. Remember, what were our three options with systems of regular two linear equations? What were the three solution types we could get?
Like, you're talking about like,
Two lines. How many ways can I lay out two lines?
they could have one solution, no solution, or
Or
infinite.
Perfect. So one solution, no solution, infinite many solutions. They could cross, right?
yes.
And the what we learned about that is that if it has any different slope ever, doesn't matter as long as the two slopes are different, they will cross somewhere, okay? Or they could be parallel lines, same slope, different y-intercepts, meaning they are never going to cross, or they could have the same slope, same intercept, and they're going to lie on top of each other, and they have infinitely many solutions for it. So in the same way that we had those three, we've got a couple of options. We've got those same options for our planes, right? So we have one solution. Here's an example of how the three different planes have met. They're meeting in one little point here. We could have infinitely many because they are crossing not at a point, but they are crossing at a line. And any line has infinitely many solutions because I can pick anywhere up and down. Remember, this expands for infinity. So when they cross at a line, they can have infinitely many. Or these are two examples. They could all be parallel, right? So parallel for two of them meant no solution. Parallel for three means no solution. Or we could have what we talked about where you could have a solution to 2 but not the third. So that means there's not a solution to that whole system. Is there a solution for 2? Yes. But is it a solution for all 3? No. So these are 2 different ways that we can have no solution. So again, same things. 1, none, infinitely many. Okay? We've just broadened it. Guess what? We solve it the same way. Substitution and elimination. Now, what I will say is that when we get to 3 equations, substitution is your hard way to do it. Whereas you might have found, did you have a preference this week when you were doing substitution or elimination? Sometimes you could look and go, oh, that system has y already all by himself. It's easy for me to substitute him in. Sometimes it was easy to go, oh, they both have a 2x in it. I can eliminate them out. So when we have it with 2, we can either go either way on it, depending upon the variables that they're given to us. I will say that whenever it comes to this way, elimination is going to be our easier way for it. Just because when we substitute, remember, every time we're substituting, we're only getting rid of one variable. So if we start with 3 and we solve for 1, how many do we have left? 2. So now we have an equation that we're substituting in 2 variables for it. But I will show both. I will say on here, with substitution, you need to use lots of brackets, lots of parentheses. So I have like my con. This can get messy with lots of brackets and combining of like terms. So you must be very, very detailed to make sure that you don't miss a step or miss a sign.
I noticed that was substitution, just in general, so I can't imagine what it's
Yes.
like with 3.
So, same thing for elimination. We're going down. Now, whenever we were dealing with 2 equations and we eliminated, we know every time we do a step of elimination, we lose 1. So with elimination, and we had 2 variables, we got to do it once because 1 elimination got us down to 1 variable. Now that we start with 3 variables, we're going to have to do it twice to get down. Because the first time that we do it, we lose 1 variable, but now we have 2. So now we have to do it again to lose that other variable. Does that make sense?
Yes.
Every step down loses 1 guy in it. All right? So here's an example of substitution. We're not going to walk through this. I just want you to see how big it can be. When I solve this guy for x, this is my new x value. Okay? So I'm plugging him in, so I had to use parentheses. Now I'm distributing my 2 to 3 separate variables, finding all of my like terms, because now I have 5 terms in my equation, solving down, and I get a z in terms of 1 variable that I'm having to then, now I have to use my third one. I have to plug x in here, and I've got to plug in z everywhere I see that. So we're just stepping down. It can get real messy. Okay? It is doable. It is not my preferred way of doing it. So we're going to work on combination. Okay? Now here's the rule. Everybody has to play. Wasn't that the rule last time? We have to use both equations, so everyone has to play the game. We can't leave a guy out. When we work with combinations, we're going to start with all of them, and we're going to pair them up. Okay? I don't care how you pair them up. They can be paired up any way. You'll get the same answer both times. I like just visually to go the top 2 and then the bottom 2. Okay? So 1 equation will be used twice. Now, if you don't like your middle equation like that, then rewrite them to where a different equation is in the middle if you want it to be. So in this guy, I'm going to pair them up. So I'm going to have 3x plus 2y plus 4z equals 11 and 2x minus y plus 3z equals 4. So that's going to be my first pair. And then I'm going to write my second pair and have 2x minus y plus 3z equals 4 and 5x minus 3y plus 5z equals negative 1. All right? So do you see how I've paired them? Now I have systems that I know how to work with. Right? With elimination, our goal is to get rid of 1 variable. What variable in this system would you like to get rid of? X, Y, or Z?
Y would probably be the easiest.
Y would be the easiest. Now here's the rule. Whatever guy you choose, if you choose Y in this guy, you have to choose to get rid of Y in the second pairing. You can't get rid of X in the first pairing and Y in the second pairing. Okay? So on this first step, we have to, whatever you pick with, you got to stay with him. He's your pitcher for this inning, for this whole inning. That's the same one. So if we're getting rid of Y here, what do we need to do to get rid of Y?
Multiply by 2.
Okay, so we're going to multiply the entire bottom by 2 and have 4x minus 2y plus 6z equals 8, correct? Erase him. Now, are we adding or subtracting those guys? Adding, okay. 3 plus 4,
7x.
these cancel, right? 4 plus 6,
10.
11 plus 8, 19. Okay, so now I have 7x plus 10z equals 19. Right? Now let's play again, do this guy. What do we need here?
Multiply the top by negative 3. Or, I mean,
Okay.
either, or no, yeah, the top
Let's
by
do
negative
negative 3.
3.
Yep. Good job. 4. Okay, so I've got negative 6x, positive 3y, negative 9z, and negative 12.
Yeah.
Great. Okay. So we don't have this guy anymore. We have the other one. Okay. We're going to add them together again. Negative 6 plus 5.
Yeah.
Negative x. These guys cancel. Negative 9 plus 5. Okay. Negative 12 minus 1. Okay. So now I have negative x minus 4z equals negative 13. Okay. Now that we have simplified, I have two equations and they have to have these same variables. Do they have the same variables?
Yes.
X and z, x and z.
Yep.
Well, now we have two equations and two variables. Can we solve that?
Yeah.
Yeah, two equations, two variables. So now this is our new pair. Okay, so here was our first step one. We went from 3 variables to 2 variables. Now we're going to go from 2 variables to 1 variable, so we've got to do it all over again. So we're going to say 7x plus 10z equals 19, and negative x minus 4z equals negative 13. Okay, what do we need to do to get rid of something?
Multiply
do
the bottom by
7.
7.
Perfect. I would multiply the bottom by 7. So I have negative 7x. 4 times 7 is 28. Negative 28. And 13 times 7 is
Like
91. Okay. So now 7 minus 7 is 0. I've gotten rid of those. 10 minus 28,
Negative 18.
18. And 19 plus
Should be
91,
110.
110. And we're going to solve for z, and I don't know that off the top of my head.
128.
110 divided by 18?
Oh, divided. It's probably like 9.
9.
Well, it can't be because 9 times 8 isn't a 0.
Negative 9.
It's not 5 and it's not 10, so it must be
You're not 9. Probably like
it's got to be a fraction, something over 9.
You get the negative 6 point
Yeah.
repeating, so
Yeah, negative 55 over 9.
Yep.
Okay? So does that make sense? Now, here's the thing. We've worked down, so we have this funnel, like this, where we get an answer. Okay? We worked down, now we just start working our way back up. Okay? So we're doing a circle. We go, because now that I have Z, I could plug him in, right?
yeah.
But now I've got to go find X and Y. Where can I use Z to find a variable that's all by himself?
You put it in 2 on another child.
The step right above it, right? So if I plugged in z to any of these, I could find x.
Yes.
And now I have x and z, to which I go back
You do it for y.
and I can do any for y. So we're just going to move our ways back
Okay.
up there. Okay? Okay,
Can I use your real quick?
absolutely.
It's a lot of erasing.
Okay, so when we have our system of equations, sometimes I like to set it up in the little T-chart just so that I can keep all my
Keep it
terms in
together,
the
yeah.
different places and they don't get messed up in it. But we want to pair them however we want, right? So we're pairing one section, but then we have to pair the other ones. We've got to make sure that everyone plays the game
Yeah.
in it. And we missed something there because I was like, it couldn't be that. It was supposed to be a negative 92. I missed a sign
Oh.
on it. So z was equal to 4. I was like, I know I missed something on it. On the fly. Okay, so the first step that we do, we're going to drop down to 2 variables. Then the second step drops us down to 1 variable. And then we just keep working our way
So you have all 3.
all the way
for the solution.
back up to it for the solution. Remember, we are looking to fill all 3 spots on that coordinate plane for it.
Yes.
Okay? Let's see. All right. So, what happens when the system breaks down? How do we know when we don't have a solution?
You know, you don't have a solution when, well, they all have to be able to equal, right? They all have to be able to equal the problem. So in that case, 0 does not equal -8, but it would have to equal -8 for it to be a solution.
Correct. So, when we are working, so here's an example. When we are working with our systems and we start pairing them. So here we do our first pair. I've got my first set is paired up. My second pair is paired up.
Yep.
All right? So when I work my first pair and I'm solving by elimination to get rid of one variable, in this case I'm choosing to get rid of the x
Yes.
value for it. So Jonathan, I made a subtraction error on that last one. What z
Okay.
is equal to 4. If you follow through the slides on it, it was
Okay.
supposed to be subtracting, not adding them for it. So we're looking at what happens when our system doesn't work. How do we know when we've got a problem? Okay, so we've paired up the first 2 guys. We've paired up the second ones. Okay, these are the 2 sets. So we're going through, here's our first step. We're going to eliminate somebody. I'm going to try to eliminate x. So I look at it and go, oh, well, I'm going to multiply 3 across here. And I'm going to get 3x plus 3y plus 3z equals 6. And now I'm going to solve for this. And I get, oh, my x is canceled, my y is canceled, and my z's canceled. And I got 6 minus 14 is -8. So I have 0 on one side and -8. 0 equals -8. Is that true?
No.
No, this is not true. So it means that these 2 lines, these planes, never touch.
Yeah.
Right? We can look at it and be like, oh, these all canceled out. Basically, all of their slopes were exactly the same and they're at a different point. So they're parallel planes that are going. They don't have a solution. There's never going to be a place where they meet. So
Yeah.
when we get something that is invalid here, 0 equals -8, they don't have a solution. They don't touch in a place. Okay? Whereas alternately, if we work these guys out here, so here's our first pair, we're going to put here. Our second pair is our blue ones. We're going to work them out. Okay, so I'm going x plus y plus z equals 2, and I've got x plus y minus z equals 2. So here's my new equation. 2x plus 2y equals 4. So I eliminated the z, so I'm going to eliminate the z here, and I've got another one. 3x plus 3y equals 6. Well, now when I work these guys the second time around, I end up with 0 equals 0. That's called your identity, right? Because that means these two equations are the same. We have an identity, so we have infinitely many solutions for him. That means they are overlapping in such a way that we've got a line or a full plane. So in this way, it actually worked out like they were the exact, we've graphed the same plane on top of each other for it. So we have an identity there. So there's a whole lot of solutions. And then those two intersect here, so basically we have a line that's intersecting. So we have infinitely many solutions. So if you get a invalid solution, there's no solutions. If we get an identity where it's true all the time, we have infinite solutions. So same as what we worked with our other ones.
Yeah.
All right? So linear programming, we're going to kind of combine a little bit of it and go back. And I did not bring your little worksheet for it. Does anyone happen to have their book? I see you have
I have
your
my book. Yeah.
Okay.
I have my book too.
Why don't you pull out your book and open it to page 163. Okay, so you guys can take this little step home. Any questions before we move on about how to solve these systems of 3 equations?
I don't believe so.
Okay. Call me if you need help, alright? Okay.
I
So-
might have to call you this week because my parents are leaving town for like 5 or 6 days.
Yes,
So
she told me.
it'll be fun.
She told me.
I'll figure it out. It'll be fun.
We'll get it. Hey, I'm available.
Sometimes my mom will send me a few of the questions on the answer key. It really helps me figure it out.
Good, yeah, to
Yes,
see how it
If
works.
you get stuck, yeah.
Perfect. Okay. So linear programming, what is it worth? If you decide to go into business, and I know both of you guys are hard workers and have business minds for that, as you're going into, we're looking at profit. Like, how can we maximize some profit? So everything that we're learning, whether it's our system of 3 equations or 2 equations, we kind of looked at that with the system of 2 equations. So like, for the stamps, how many stamps should he do? If I'm catering and I'm having this amount of food, how do I get the most food for the amount of my money and feed everybody? That's what we're doing. We're trying to find, how can I spend my money and get everybody fed? How can I use all the stamps that I have and get the cards out that I need? Those were with 2 equations. So as we get more, we have 3 equations, maybe 4 equations, some different things. We're basically using our system of 2 and 3 inequalities to decide, where should I invest? What should I invest a little bit more in better tires, or should I get better windshield wipers? Should I do, like, what's gonna get, like, is it worth it for me to get the premium gas depending upon my gas mileage? Or is it not? Like, what's my cost savings for it? Like, should I get the extra bobo in my tea or not? No at all choices from Ms. Thomas for it, okay?
Have to get
So-
premium gas sometimes.
Yeah,
Yeah.
sometimes, like, you just don't know. So linear programming gives us this bounds, and then we're gonna work within them, okay? So I'm gonna work through one here, but I want you to kind of see the visual, and then if we have a little bit of time, we're gonna work through that.
Okay.
There is a small worksheet that I have on our Google Classroom that is your homework to print for that, and but you just choose one. It's a choice board, and so you just choose one of them, okay, to work through. So in this one, it says Kim wants to knit and sell hats and scarves. So she's selling hats and scarves. So as we are working through, remember, we're wanting to identify everything that it has. It says a hat uses 6 ounces of yarn, and a scarf uses 9 ounces of yarn. And she has a total of 72 ounces of yarn that she can use up, okay? She wants to make at least 3 hats. So we've got hats needs to be what? Greater than
greater than
or equal to 3, right?
Yes.
So we've got a couple of different things that we can work out. So if we've got hats, we know that our hats has to be greater than or equal to 3. How do we do this? We've got ounces and ounces and ounces. How do we make an equation or an inequality that talks about using up the yarn that she has? Can she use more than 72 ounces of yarn? No. So she has to use less than or equal to 72 ounces of yarn. So if could I say she's got the ounces of hats, right? Plus the ounces of scarves has to be less than or equal to 72 ounces,
Yeah.
right? So how do I get my ounces of hats?
You would move the ounces of the.
And we're just writing out our equation. So for each hat uses 6 ounces,
Okay.
right?
And plus
Plus
9 for every scarf.
9 ounces for each scarf has to be less than or equal to 72
Okay.
ounces, correct? And I have hats is also equal to, has to be greater than 3. Now what about scarves?
We don't have anything.
So what could I say about scarves? Scarves, how many scarves, what's the least amount of scarves that she can make?
9 ounces? Wait, no.
The least number of scarves that she could make. Zero. Right?
Oh, yeah.
So if she's going to make scarves, she's going to make greater than or equal to 0 scarves.
Yeah.
Right? So now we have an equation. We have an inequality that addresses our hats. We have an inequality that addresses our scarves. And we have one that addresses them together. Right? So if we are going to put these together, we're going to use a coordinate plane. Right? So the first guy we're going to do is we're going to put up hats. Hats is greater than or equal to 3. So how do we graph him? Let's do that. Greater than or equal to 3. So hats. If this is our hats, we'll call it the X and we'll call this guy Y. Scarves over here. So hats is greater than or equal to 3. So if hats is equal to 3, we put it there. Greater than means.
It's a full line. Oh, yeah, it goes
Yep.
there.
I am shading all of these guys over here. Right?
Yes.
Scarves is what?
Anything greater than 0, so.
Yep.
it's just
And these
gonna
guys
go
are going to
there.
have to move. Okay. Scarves is anything greater than 0. Right?
Yes.
And now we have this linear equation over here. So let's solve him. Let's replace this. 6x plus 9y is less than or equal to 72. I needed a line, so I need to solve for what?
Y.
Y. Okay, so 9y is less than or equal to negative 6x plus 72.
Divide 9 from each side.
Y is equal to negative 2/3 x plus 8. Agree with that?
Yes.
So there's my line. 2/3 x, I've got a slope, plus 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to start here and I'm going to go down 2 over 3. Right? Down 2 over 3. Down 2 over 3. Okay, so here's my line. That goes through that. Y is greater than, or less than, so I'm doing the part underneath. So what part gets all 3 of those guys?
That's
This
the
whole
inside of it,
triangle, right?
Is there a part that. Wait. It hits all 3?
Uh-huh. So my,
Okay, you mean inside, not a point. I
Yeah.
get it, yeah.
well, and even up to the points. Okay? So now, the important thing is now that we have bounded our space, these vertexes are our important values. Okay? So this first vertex is 0, 3, 0 scarves and 3 hats, right? This one is, we're going to look at where we're at, and it's at 3.6. And this guy over here, we've got another, it's like 0, I think it's like 12 or something like that. Right? So now it says, how many hats and scarves should Kim make to maximize her profit? So now we're going to look at profit. Profit is the money from the hats, let's call them X, plus the money from the scarves. Right?
Yes.
So it says a profit on a hat is $10. So she makes $10 for every hat. She makes $20 for every scarf. Okay? Is our profit. Okay? So now that we have our profit equation, we use our vertices and we plug them in and we find out which one gives us the most. Okay? So if we've got 10x plus 20y, and I plug in 0 and 3, so I've got 0 and 3, how much profit does she make down here? $60. Right? How much profit does she make up here? At 3.6.
So 150.
150. Okay? And that one is it. Yeah, I think it was 12. So we know that because it also said that she wants to make at least 3 hats. All right, so that gave us 3 hats and it gave us 6 scarves. She made 150. We can see that anything that goes down, we've got more hats, but she's got less profit for it. So this is our maximum profit. She's going to maximize her profit by making 3 hats and 6 scarves. Okay, so our vertices give us the value where we're going to plug in and actually find it for our profit. So that's the whole thing for dealing with our linear programming. Sometimes you will see a graph already done like this, and it'll say at what place do you have the maximum profit, or what place do you have the maximum. There's a one in your examples that talks about him flying in a plane. But when we graph it, I wanted you to look at your graphs and see that sometimes, does it have to be just simple 3 equations? No, we've got that guy that says it's got an unbounded region. Right? And so he's got 3 separate, maybe 4 separate equations that are all of his different bounds, and he's got a huge region, and so we're trying to find all of the different places that it could be. You know, and then remember that we can't have negative profits, things like that. So I just wanted to expose you guys to that because sometimes that is something that you will see later on, and if you've never seen a linear program or you don't know which part of it to solve, it feels overwhelming, but we are going to graph it exactly like a system of equations or a system of inequalities. We're going to graph it, find the place for all the overlaps, and then the places that are the most important to us are the vertices of any of the places where it touches. Those are going to be, because otherwise you're putting in, 20 to 50 different options. Where do I pick somewhere in this graph? So we're going to have to look at the vertices to find out where to pick in that graph. Right? So that is it. Your homework for this week is to finish up your